To the naked eye, our world appears orderly and stable. A glass of water resting on the table looks still, but if you zoom in on the atoms and molecules that compose the water, you would see that actually they are moving. The microscopic world of fluids is animated by countless particle collisions, moving atoms and molecules on wandering trajectories. This random movement of particles is called Brownian motion. In 1827, botanist Robert Brown first discovered this phenomenon after observing that pollen grains jitter when immersed in water. For several decades, it was unclear why small particles would dance when suspended in a fluid. Some scientists thought that there was some sort of life force driving this movement, since pollen comes from plants, but it was soon discovered that non-living materials, like dust and iron filings, exhibit the same jiggly behavior. In 1905, the mystery began to unravel. Albert Einstein modeled the motion of Brown's pollen particles as a result of being bombarded by individual water molecules. In Einstein's model, the water molecules bombard a pollen grain from different directions, some directions more than others, resulting in its seemingly random motion. While ancient Greeks and Romans had theorized about atoms and molecules, Einstein's work validated the centuries-old idea that units of matter too small for our eyes to see actually do exist. By understanding Brownian motion, Einstein was also able to accurately determine the size of atoms and molecules. Brownian motion can explain a wide range of processes, such as the movement of bacteria and proteins, the diffusion of calcium through our bones, the spread of pollutants through air and water, and even the movement of viral particles through the air. Scientists also use mathematical models of Brownian motion to describe fluctuating social phenomena, such as stock prices, the transmission of disease throughout a community, and the spread of rumors in social networks. This is because human behaviors, like Brownian motion, involve randomness. Many of the decisions we make about things like buying stock or socializing are influenced by a combination of innumerable complex factors, such as the weather, what we ate for breakfast, or whether our neighbor said hello to us on the street. Brownian motion also plays a central role in recent and emerging technologies, particularly those that depend on the process of diffusion, the movement of particles from an area of high concentration to an area of low concentration. Brownian motion is integral to understanding diffusion since the latter involves small particles suspended in a fluid. Exciting applications of diffusion include generating energy from salinity differences, designing dialysis machines for removing waste products from blood, creating batteries for storing energy, and desalinating water to make it potable. Despite operating on a minuscule scale, Brownian motion is fundamental to understanding how our world functions, and it will continue to play an important role in the technologies that will shape our future.